Hey guys, welcome back. In this video, we are going to go through Chapter 7, Section 1, Estimating a Population Proportion. So the background here is, imagine the following scenario. It is time for a new presidential election. During the weeks before the election, pollsters are busy collecting data as to how they believe the voters will vote. They survey people across the country, calling them, doing online surveys, people from different groups, religions, genders, income levels, race, etc., trying to get a true random sample. So periodically, they will publish their results. Often on a TV, you will see Fox News, CNN, anyone saying that their prediction of the percentage of voters favoring each candidate, and at the bottom of the screen, you'll often see a margin of error, often 5%. This is the essence of what we are trying to accomplish in this unit. We will have some information relating to a sample, and we will try to predict a value for the overall population using that small sample. So here's a simple example. So say you decide to check the proportion of red M&Ms. A sample of 100 candies has 21 red ones. Okay, so this sample obviously contains 21% red M&Ms. However, we know that we cannot simply say that out of all the M&Ms in the world, which would represent the population, that 21% of them are red. So the 21% is what we call a point estimate. Without any further information, this is the best estimate that we can provide. However, we know that this is only the probability within that sample, not necessarily of the entire population. So a point estimate. A point estimate is a single value used to estimate a population parameter. The sample proportion, which we call or denote as p hat, that's a very scientific name to call that little thing above the p hat, is the best point estimate of the population proportion p. Okay, so to say that again, sample proportion is p hat. That is the value that we have based on the sample. And we are trying to use that sample proportion to estimate the population proportion. So think of the sample proportion of the M&Ms is the p hat, the 21%. The population proportion p, we don't know, and that's what we're trying to figure out in this section. So the best point estimate for the proportion is the p hat, which is denoted by x over n. X is the number of successes within your sample. N is the sample size that you have. Okay, so the goal of this section is to take a sample and use it to predict or estimate values, which is a way that we call it parameters, for the entire population. Now, if we were somehow able to survey everyone in a population, we would be able to accurately calculate parameters without needing the predictions. However, obviously we know that surveying an entire population is not practical, so we use a sample. Since we are only working with a sample, we cannot know for sure what the actual parameter of the population is. Therefore, we can only provide a confidence interval for where the actual population parameter lies. What's a confidence interval? A confidence interval is a range of values in which the population parameter of interest should lie. So basically, it's like, how confident are we that the interval we calculate actually does contain the population parameter? Typical levels that we use are 90%, 95%, or 99%, aka also known as we are 90% confident, 95% confidence, 99% confidence. We are that much confident that the actual population parameter lies between a lower limit and an upper limit. So to say that we are X% confident of something, we need to look at a normal distribution. So let's just, for now, look at 90% confidence. 90% confidence means that we are interested in the parameter actually falling within the z-scores that contain 90% of the normal distribution. So 90% might be from here to here, and the area under here would be 90%. We're interested in our population parameter falling somewhere within the z-score lower limit, the negative z-score, and the z-score upper limit, the positive z-score, to contain the value of interest. Okay, so how do we find those z-scores for the confidence intervals? The yellow shaded region is our confidence interval. This would be our lower z-score, this would be our upper z-score. The green region is the area outside of our confidence interval. Alpha represents the probability outside of the confidence interval. Therefore, say we are interested in a 95% confidence interval. Alpha would be 0.05. Now, since there's two green sections, each of these would constitute half of the total alpha value. So if the green total area was 0.05, then each of these, the left tail and the right tail, would be alpha over 2, or in this case, 0.025. It's always going to be half of the total green area since there's symmetrical left and right tails. Okay, so let's find that critical value. So find the critical value, z of alpha divided by 2, corresponding to a 95% confidence level. So alpha would obviously be 0.05, alpha over 2 would be 0.025. You multiply that by 2, you go back to your 0.05. The figure on the next slide shows that the area in each of the green shaded tails would be 0.025. Then you have to use the table A2, and you will find that that corresponds to a z-score of 1.96. You can also use technology, and you'll find that the confidence interval, 95% confidence level, the critical values would correspond to a z-score of positive and negative 1.96. This is just kind of giving you a little bit of a graphic of that. So 95% confidence level shows that the area under the curve that is yellow is 0.95. Each of these little tails is 0.025. And then we want to know, hey, what z-scores will divide this total normal distribution up the way we are interested in. And we find that it is negative 1.96 and positive 1.96. Now, same thing for a 90% level. What would that correspond to? Well, 1 minus 0.9 divided by 2 is 0.05. We use a z-score. We find that it's negative 1.645 and positive 1.645. I encourage you to use the table A2 just to verify, okay, I know where those numbers came from. I know how to use this chart. The 95% level we just did. That gave us a positive and negative 1.96. And then the 99% level. Same concept with using the z-scores. And then you find that it's negative 2.575 and positive 2.575. Here's a little summary of that. And these are the three that we will be using most often. Occasionally, you might get a 80% confidence level, a 98% confidence level, but 9 out of 10 times, you'll probably get one of these three. Okay, margin of error. The confidence interval is denoted or determined by calculating the margin of error E. And E can be found by multiplying the critical value that's the critical value is what we just calculated previously, and the estimated standard deviation of sample proportions. Long story short, here's your formula. You have E, margin of error, is equal to the critical value multiplied by the standard deviation of the sample proportion, which is the square root of P hat times Q hat divided by N. What is P hat and what is Q hat? Well, let's look at what each of the symbols means. Capital P is the population proportion. We don't know that. Remember, we only know the values of our sample, and we are trying to use our sample to find the population proportion of the overall entire population, everybody. N is the number of trials or observations within your sample. X is the number of successes within your sample. P hat is a sample proportion found by X over N. It's the a probability of success. And we round that to 3 decimals. Q is the proportion of failure, which is, if you remember from stats 1 minus P hat. So P hat plus Q hat should equal 1. It's binomial. It's success or failure. And then this critical value is the z alpha divided by 2. We just did that in the previous slides. If it was a 90, 95, or 99% confidence interval, these are the values you would use for your z right there. All right, if you're like me, all those slides are great, fine and dandy, but let's look at an example and then we will really have it seal the deal. We survey 100 people. We ask them, do you smoke? 20 people respond yes. Based on the survey, what proportion of the population smokes? Now you can't just say, oh, okay, well, I interviewed 100 people, 20 said they smoke, therefore 20% of the entire population smokes. You can't just say that. 20% is a good starting point because that would be the sample proportion. But we want to know, how can we estimate the population proportion? So let's find the 90% confidence interval, 95% confidence interval, and 99% confidence interval. Let's start by giving some numbers. Okay, we have 100 people, so our sample size is n. X is the number of successes within our sample, 20. P hat is the sample proportion, which would be 20 over 100, or 0.2. And then Q hat would be 1 minus that value, or how many people responded no. So 80 over 100, or 0.8. Another thing to note is that in order for us to be able to do this, P hat times n must be greater than 5, and Q hat times n must be greater than 5. If it's not, then we say that the equation kind of falls apart. You don't really get reliable data. That's just kind of a side note. Okay, so let's go back to our equation. Margin of error equals the critical value multiplied by the standard deviation, which is square root of P hat Q hat divided by n. And this is how we represent it. Now this might look a little confusing, but let's just break it down. We are saying that the sample proportion minus that margin of error is less than the population proportion, which is less than the the sample proportion plus the margin of error. So another way of saying that is the population proportion is in between the sample proportion minus margin of error and the sample proportion plus the margin of error. And we are however much % confident that that statement is true. So 90% confidence interval. 90%, z is 1.645. Let's go back a few slides to show that. 1.645, 90%. Multiplied by 0.2 times 0.8 divided by 100. Margin of error is 0.066. So 0.2 minus 0.066 is less than P, which is the population, which is less than 0.200 plus 0.066. Therefore, we are 90% confident that the population proportion falls between 0.134 and 0.266. We can also check this using our TI calculators. I encourage you to do this as well. Press Stat, go over to Tests, then go all the way down to A, where we say 1 proportion Z, fill in X, fill in N, fill in the confidence level. One thing to note is that X and N must be integers. Go to Calculate, boom, 0.13421, 0.2679. Look familiar? That's pretty much what we got over here once you account for rounding. Do the same thing for 95%. Now this part is going to be the same, the 0.2 times 0.8 divided by 100 square root of all that. What's really going to change is the critical z value. When we do it for 0.95, z is 1.96. Follow the formula, and we are 95% confident that the population parameter falls between 0.122 and 0.278. Then we go up to 99%, z increases, and you can see that as you become more and more confident in something, the intervals get larger and larger. And that just makes sense intuitively that the less confident you are of something, the more tighter that interval is going to be. And the more confident you are of something, the wider that range is going to be to encompass more possible values. Okay, interpreting a confidence interval. We must be careful to interpret confidence intervals correctly. There is a correct interpretation and some not proper ways to word this. So the correct way to say we have this confidence interval including the margins of errors, and we want to be able to word this correctly. So the correct way to read this is we are 95% confidence that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. Now here are some wrong ways to read this. We cannot say there is a 95% chance that the true value of P will fall between 0.405 and 0.455. Another wrong way of wording this is to say 95% of sample proportions will fall between 0.405 and 0.455. Okay, so let's go through the steps that we just did. Confidence interval for estimating a population proportion. The requirements. The sample is a simple random sample. It cannot have bias. It must be good quality data. 2. The conditions for the binomial distributions are satisfied, meaning that there is a fixed number of trials. The trials are independent, meaning that they don't rely on one another. And there are 2 categories of outcomes. It is either a success or a failure. It cannot be both. Like in the previous example, you either smoke or you don't smoke. We're not interested in people who say, well, I'm a casual smoker, or sometimes I smoke, but I wouldn't call myself a smoker. No, it's yes or no. It is binary. And the probabilities remain constant for each trial. And we really would need at least 5 successes and at least 5 failures. That'll give us a good indication that our data has enough of a sample size to have a somewhat reliable conclusion. Okay, so just some ways to express confidence intervals. You can either say p hat minus margin of error is less than the population proportion, which is less than the sample proportion plus the margin of error. You can also express it either of these 2 ways, where it is the sample proportion p hat plus or minus the margin of error, or we can express it as this kind of interval notation. So, procedure for constructing a confidence interval. Verify that the requirements in the preceding slides are satisfied. That would be these requirements. Use technology or table A2 to find the critical value, or if it happens to be 90, 95, or 99%, you know those. Evaluate the margin of error, and then using the value of the calculated margin of error and the value of the sample proportion p hat, now we can create that confidence interval limit by the sample proportion minus the margin and the sample proportion plus the margin of error. Okay, 3 different ways to find the margin of error. We did the equation. You can also use the calculator, and you can use StatCrunch, and I provide YouTube links and steps for that as well. And then finally, we'll just do one more example. We note that a Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook pages. So the sample results are n equals 1,487, and the sample proportion is 0.43 for p hat. Find the margin of error that corresponds to a 95% confidence level. Find the 95% confidence interval estimate of the population proportion P. Based on the results, can we safely conclude that fewer than 50% of adults have Facebook pages? Okay. First, we got to check the requirements. We are going to assume that it is a simple random sample. You either have a Facebook or you don't. And then we have enough data to prove that we have at least 5 successes and 5 failures. Requirement check complete. You can do this, again, like I said, from StatCrunch, the technology, or from the formula. So we can conclude that the margin of error is E equals 0.025. So the confidence interval would give us these values. It would be the 0.43 plus and minus that value. And here's just showing the StatDisk calculation. You can also do this again using the formula that we did on a few slides previous, and you find that you get the same margin of error value. So then this would be your confidence interval. We are 95% confidence that the actual population proportion lies between these two values. Based on the confidence interval obtained in Part B, it does appear that fewer than 50% of adults have a Facebook page because the interval of values from 0.405 to 0.455 is an interval that is completely below 0.5. There's your summary. And then other types of problems. You may be asked to find the point estimate and margin of error from a confidence interval. In this case, you are given the confidence interval, and I want to know the point estimate or the margin of error from that. So if you have the confidence interval and you want to find the point estimate, you do this equation, which is just the upper confidence interval limit plus the lower confidence interval limit divided by 2. Gives you the average of the two, which has the margin of errors cancel out, leaving you with just the sample proportion. Or you can do the margin of error, which is the upper confidence interval limit minus the lower confidence interval limit, which would then cancel out the point estimate. So then when you divide that by 2, you get the margin of error. So the article, High-Dose Nicotine Patch Therapy, includes a statement. Of the 71 subjects, 70% were abstinent from smoking at 8 weeks. We are 95% confident. The 95% confidence interval has a lower limit of 58% and an upper limit of 81%. Use that statement to find the point estimate p hat and the margin of error. So just using those two equations, the upper confidence interval limit plus the lower confidence interval limit divided by 2 gives us a sample proportion of 0.695, and then the margin of error can be found by doing the upper confidence interval limit minus the lower confidence interval limit divided by 2, so the margin of error is 0.115. Finally, we may want to find out the sample size needed. So we are given a confidence level, and we want to know we are given the confidence level, amount of allowable error, and a sample proportion, and we want to find the required sample size. How many people do we need to interview, survey, in order to be able to have that given confidence level, error, and sample proportion? So we work backwards, and we use the formula to now solve for n. So we want to determine the sample size for the proportion of smokers at 95% confidence with an error of 3%. Find the required sample size if a previous study indicates 20% of people smoke. Okay, so here's your problem. Here's your formula. We have 0.2 people as the 0.2 value right here for the sample proportion. Q hat would be the 80%. The Z would be the 1.96 because of the 95% confidence critical value divided by the margin of error is 0.03 squared, and you would have to get this value. Obviously, you have to round up since you can't interview 0.95% people, so you would have to survey 683 people. All right, that concludes this section, guys. Thank you.